Hi, today we'll be doing an implementation on a linked dropout stack. So in the last video we did an implementation of a linked stack. So this is the continuation of the Java data structures series. So what is a linked dropout stack? So a linked dropout stack is a data structure called a linked dropout, or just called a dropout stack, that behaves like a stack. In every respect, except that the size is fixed. So there's going to be a fixed size. We're going to have a variable for size. If the stack size is n, the bottom element is dropped out when the n+1 element is pushed onto the top. So we're going to be using links. You can also use an array to do it. So I'll just delete that. So a link dropout stack, we're going to be implementing that. It's going to use the StackADT interface as well for a stack. So we can save that, and it's also going to use the linear node class. So see the previous video on the link stack if you want to see how we implemented this code. There is a code in the GitHub file. I'll try to upload that. If not, just see the previous video. We do it step by step. We talk about everything, so that way you aren't confused about what's happening. So we're using those classes. We'll probably use the empty collection exception. I don't know if I've uploaded that, but we will, because I updated the link stack. I did a video on it. I'll get that uploaded soon with the diagram. So see the diagram as well. Watch how the nodes are being put on and taken off the stack, and how the links are working. So we'll start writing the code. So for this class we just have public class dropout stack. We're going to be using generic types again, so of generic type T, and we're going to implement our StackADT interface. And we're going to get an error because it's telling us that we haven't implemented the methods. So we're going to have a private int count variable, and a private linear node of generic type T variable named top. Again, we're going to have top, and then we're going to have a private int stack size. So the only difference here is I think we're just having excuse me, the stack size variable. So this just tracks the size of the stack. Before we didn't have a stack size, we just had a count, so we didn't keep track of it, I think. So we'll do the constructor now. So again, to do a constructor, you just call the class name. Instead of generic type T, we just open parentheses, and then we pass in the parameters here. So int stack size, we're going to pass a stack size in the object when we instantiate our dropout stack object, which is our data structure. We're going to pass in a stack size variable as a parameter for the fixed size. So here we'll set count equal to 0. top set to null. It already was null basically, I think. But here we're just showing that it is. So this dot, we're going to use this keyword here and set this dot stack size equal to stack size. So what's happening here is it's saying this instance data stack size is set equal to the parameter stack size. And that's it for the constructor. I did this code a while ago. It was a code for data structures, the class, the university class, data structures, which was based on Java. You can also do it in C. I think I did it in C a long time ago, like several years ago. But they use pointers and stuff, so it's a little bit different, but a lot of it's the same. I didn't write any Java doc for this, so I will just be writing the methods. Most of the methods, they all do the same thing anyways. They're just different. They're just implemented differently. So we'll write the public push method. So public void push. It takes a t element as a parameter. Here we'll create a linear node. We'll call it node and set it equal to new linear node. Pass an element as a parameter. And we'll say if count is equal to stack size. Then here we'll create an object reference variable of type linear node, named temp node. We'll say temp node points to top, so the top of the stack. We'll say while temp node dot get next. So remember, the next reference in the stack is technically a previous reference because it's pointing backwards. Because in a link stack implementation, the next reference actually points backwards. So you can think of it like a previous reference. It's easier to think of it like that. They should have just I guess they were in the textbook Java Foundations they were using before linked lists. Before they actually explained it, they taught the link stack first. So I guess they were trying to get us used to the next pointer. So anyways, it just starts at top, and it's gonna right here. We're gonna do a traversal. So the best way to do these is use the debugger, set a breakpoint, and watch the nodes traverse. We do an example of that in the previous video, link stack. We'll try to do it in this one as well. So here we just have while temp node dot get next. Does not equal to null. So this time we're using the get next. I don't think we traversed. Did we traverse? We might have in the toString, but maybe we didn't go over it. So get next is a method from the linear node class. Right here, it just returns next for the node. It returns the next reference for this node. So while temp node, which is pointing to the top node, so basically while top node dot get next does not equal to null, then we're going to say temp node. So while temp node dot get next does not equal to null, and we're going to say and temp node dot get next does not equal to null. Then we're going to say temp node points to temp node dot get next. So this is kind of confusing, but all it's saying is while the top, in this case, while the top's, since temp node's pointing to top, it's saying while temp node or top dot get next. So top, if we have nodes here stacked on each other like this, like cubes, up to down, the top element is the top node, correct? So we're saying while the temp node dot get next, so the cube under it, or the node under it, does not equal to null, and the cube under it and the cube under that does not equal to null, then temp node points to temp node dot get next. I think the reason why I did that because there was a bug. So I think at some point it was probably throwing a null pointer exception, so I did this because of that, and we're gonna debug it, so we'll check that later. Don't worry about it. If you don't understand, we'll come back. I think that's right. I can't remember why I did that because I wrote this a while ago, but I'm not sure why I did that, but we'll come back. We'll debug it to see what's happening anyways. So then here we'll say temp node dot set next to null. So while temp node dot get next does not equal to null, and temp node dot get next is not equal to null. So here it's just looking at the next element beside the node that we're currently at, and then here it's looking at the next two elements. So basically the next element and then the next two elements does not equal to null. Then temp node points to temp node dot get next. Temp node dot set next null. Count minus minus. Okay, so we're dropping out the stack. Okay, so what's happening here is basically if our stack is full, so if count, right, if our count variable here is equal to stack size, so let's say we instantiate this and our stack size is like 5. Then here, if count equals 5, then it's going to enter this condition here. It's going to create these nodes here, the object reference variable, set the object reference variable to point to top. So if there's 5 elements now, right? 5 nodes, 1, 2, 3, 4, 5. So if 5's the top element, so while temp node, which is pointing to the top element, which is 5, dot get next is not equal to null. So if, while temp node, so temp node here is the object reference variable. While temp node points, so temp node points to top. While temp node, which is pointing to top, dot get next, so it's asking if 4, while 4 does not equal to null, and temp node dot, so this is temp node, which is top, dot get next, which is 4, dot get next does not equal to null. Then temp node points to temp node dot get next, so now temp node is this one, and top still 5. Temp node, so it's going to continue to do that. So now it's a while loop, so while temp node, which is here now, dot get next, which is this one, does not equal to null, and temp node, which is this, dot get next is not equal to null. Temp node points to temp node dot get next, so now this is actually temp node now, so we're traversing here in a kind of a slightly different way. So now temp node's there. It's not here anymore. So now we're back up at the condition. So while temp node dot get next does not equal to null, so while this 2 does not equal to null, and temp node dot, which is this, dot get next does not equal to null, temp node points to temp node, which is 3, dot get next. So temp node's now here. Sorry, it took me a sec to kind of remember what's happening, because I haven't looked at this in a while. So I hope it's helping so far. So then temp node's now at 2. So we're at the condition again, because we just did that. We traversed from 3 to 2. That line was executed, then we come down here. Then there's nothing else, so it loops back up like this to the condition again. With the debugger, it can be kind of confusing. So then we just say, well, temp node dot get next, so temp node's here. Dot get next, it's at 1, or it's asking, so temp node's at 2, right? Well, temp node dot get next, which is asking for 1, does not equal to null, and temp node, which is 2, right there, dot get next, which is 1, dot get next, which is null. So that condition is actually false because it is null, because this one's skipping 2 elements and this one's skipping 1, so we only have 1, and then 2 is null. So it wouldn't traverse in that case. It would skip this, and it would say temp node dot set, which is here. Temp node dot set next. So we're at here, right? Temp node dot set next, which is 1, to null. So it's going to drop out. This was just our imaginary null. This was 1. That one becomes null. And again, with the debugger, we'll be able to see it a little bit better. So that's what's happening here. Then we're going to decrement count by 1, and that's it. I guess that's why this was written, because that's how it checks. So probably when I wrote this code, it was like getting an error when it got to the bottom, because it was probably dropping out the element. It's probably dropping out the second last element or something. That's why you just have to play around with it. Like, excuse me, you may have to like do like get next, test it, see if it worked, and if it didn't, you may have to like skip to do a get next or get next. So that's a method chain. After you get used to it, it'll come naturally, but you'll just be writing temp node.get next, and then just take the parentheses, and then you can tag on another method with a dot operator, and you can actually keep doing that like that. You can keep going get element, get next, whatever. So just play around with it. So then now after, we'll just do we'll say node dot set next to top, and then top points to node count plus plus. So we have our node creation here, if count equals the stack size, got all that, then the loop finishes, and then we do those 3 lines. So we'll run through that in the debugger. So everything else is pretty easy. It's actually the same as the link stack. And I think this is for the pop method. This is the book way, but I think I changed it. So we'll change it as well. So here we'll create a variable of type t. We'll set it equal to, or we'll point it to top.getElement. Then we'll say top points to top.getNext. We'll decrement count. Whoops. Then we'll return val. I think we changed that. So what we can do to make it, to save memory, to make it more efficient. One sec, let me just check. So what's happening right now is it's still leaving the node out there. It's just not really connecting it to the link stack. So what we're gonna do is we're gonna set the node to null. That way we'll save the memory for something else. So it's gonna free up space basically. I think it's the same method from the link stack. So tResult points to top.getElement, top points to top.getNext, count minus minus, and return result. Yeah, it's the same thing. So here we'll just check for exceptions. So actually we haven't written is empty yet. That's okay, we'll just write it. So if is empty, we'll say throw new empty collection. Actually, we don't have to do that, but we can. We'll just do it now, since we're already doing it. But it's optional to just print out an exception occurred, and you can return null if you don't want the exception process to occur. See the previous video on LinkStack if you're interested in that. Actually, no, I haven't uploaded that. I will. It'll be called Part 2, LinkStack Part 2. So just look out for that if you're looking. Here we'll just say throws empty collection exception. Then here we'll just create a linear node of generic type t, object reference variable named temp. We'll set it pointing to top. Tval, that's all fine. Top points to top.getNext. Or getElement, sorry, top, then top points to top.getNext. Top points to top.getNext, and we'll say here we'll say temp points to null. So again, the way to think of this variable is like it's controlling top. So here we're going to set top to null. Because again, everything moves from the top of the stack, right? You add an element to the stack and you remove it from the same place. So when you add elements to a stack, you remove from the top and you add to the top. So that's why it's we're setting top to null. So top points to top.getNext. So we're setting temp to null because temp is actually pointing to top. But it's not actually going to change because top's pointing to something as well. So it's not like just it's going to actually just go right through to the first element. It's not going to change top itself. But we can change that if we need to. We'll check it in the debugger if we have to reset top anyways. But anyways, we have linear node temp pointing to top, tResult points to top.get element, top points to top.get next, 10 points to null, count minus minus return result. So then here we'll say we'll create the next method, so public t peak. Again, we can say throws empty collection exception. Whoops. Empty collection exception. Oh, that's okay, because we did do that. We did, sorry, just going back to this method, we did reset top, I believe, so it should be okay. We'll just double check that after in the debugger, so I'm not trying to imagine all those memory locations. So public t peak throws empty collection exception. We'll say if is empty. I guess we could just do it the other way here. So that's off. We could just say that's optional. Optional to throws empty collection exception. We'll just call if is empty. Then we'll just system.out.println stack is empty. Then we'll just return null. That's another way you can do it if you want. If you don't want to cause an exception process to occur, because the program will just basically it's going to crash when that happens. So if you want it, you want the flow to continue, you can just do something like that. So here we'll say return result. Actually, no, sorry. Do we say no, sorry, return top.get element. So returns the peak, returns the element without modifying it. So that's what we're doing here, just return the element and don't modify anything. So here we'll write is empty. So public boolean is empty. Return count is less than or equal to 0. So here it just returns true if count is less than or equal to 0. Here we'll do the size method, so public int size. So just return count. Actually, we could have returned stack size as well, but that's fine. Actually, whoops, just double check. So we have return top.get element for peak. Return count is less than or equal to 0 for is empty. Size return count, yeah, that's all fine. Then we'll just do the toString. So we don't just get memory locations when we print it out, or hash codes. So public string toString. We'll call the command here, so add override. So it's going to override the, I think it's in the object class. ToString was defined in the object class, I believe. So we're going to override the object class's version here and write our own. So we'll create a string variable that's empty. And we'll create an object reference variable here. 10 points to top. we'll say while temp is not equal to null, system.out.println. Actually, no, do we? We could print it, or we could concatenate it. Concatenating is usually better, because sometimes a print can cause an error. So we instead of doing that, I mean, I guess we could do it another way than the link stack. So before we had str points to str plus top sub, so str points to str plus temp.getElement plus new line, and then temp points to temp.getNext. So we can do that actually. So it's a good way to do it. So str equals to str plus temp.getElement. Then we'll say temp points to temp.getNext. And if this doesn't work, we can just do a backup line for later, just in case. So we'll say system.out.println temp.getElement. Sometimes this way won't work though properly, so this way could be better. So that's fine. We'll just keep it like that. str points to str plus temp.getElement plus new line. The reason why we do it in a new line, we add a new line, is to print it out like a stack. So every line is something, but you can change it if you want to just do left from right, where left is the bottom of the stack and right is the top, but we're doing top is the top and bottom is the bottom. So then here, don't forget to return str to satisfy the string return. That's it. I think we have everything. Should be everything. So now we'll just go to main. Should be fine. Those errors went away because we implemented everything, so we'll go to the main method. I have some try blocks and catch blocks set up. You can copy those if you want. Whoops. So we'll create a dropout stack object. So dropout stack. Just call it like that. Dropout stack. Dropout stack. Whoops. We need a type, or else it's gonna say. See if we'll go back. Then it's gonna say it's a raw type. I think. Yeah. So we're not creating a raw type. We're gonna create a. We can do string as well, I guess. So dropout type of type string. Dropout stack points to new dropout stack of type string objects. Takes a size. I think, yeah, it does. So we'll just take 5 as a size. So we'll say dropout stack dot push. Excuse me. we'll push the, actually no, it's a string, so we'll push the string 5, not the integer. We'll push, we'll push a few. We'll push 6 now. I guess we'll fill the size so it shows the why don't we do the size 4 then? We'll change it to 4 and then we'll do 5 elements then, so we'll just copy this. Actually, we don't have to copy it. DropoutStack.push, we'll push 11 on. I use these numbers just because I use them to test. Pretty much use the same ones to test. $13. The string though, not the number. And we'll just test one more. Actually, yeah, we need one more. So we'll just put like 10 million or something, just to see the string. So now we will set a breakpoint, take that one away. So what's going to happen again is we're going to push 4 elements on, and once the stack size is set, it's just going to push the last one on, and it's going to drop 5, and it's going to push this one on, and then it's going to keep 4, and every time we push another one on, the next one's going to get dropped. So we'll click the debugger. Excuse me. Okay, so you can see our variables here. Or sorry, not our variables. Actually, we can go back. So I'm just gonna take a sip of my water. Excuse me. So yeah, sorry for long videos. I'm not gonna cut all this stuff out because it takes too long, but may take a sip of water here and there. Also you should too. Stay hydrated. Okay, so we're here. So actually we'll stop this and we'll move our breakpoint here, just to show our object instantiation. So I don't know why it's so small. Their interface is small. Like I don't think I can change the size of that text. But you can just try to full screen it, and if not, just zoom in. So we'll step into that line. So again, we're instantiating a dropout stack. So we're going to go into the dropout stack class, right to the constructor. So it took a size of 4. We're in the constructor now. So we'll step in. So count is set equal to 0, because it has instance data up here, right? So count is set equal to 0. Top equals to null or points to null. Then this dot stack size is set to the stack size passed in, so stack size is now 4. That line's down our object is created. We can see dropout stack here at memory location 950. We click on it, it has its instance data as up here, count, top, and stack size. All its fields are there. We're at this line now. We can step into it. So here we're going to create a linear node object of generic type T, call it node and set it equal to new linear node of generic type T, and pass in the element 5 or the string 5 into element basically. That's it. So the parameter that we passed into main 5, the string 5, is going to get passed into here by calling that variable, because that variable was instantiated here, T element, and we're calling element in here and passing the parameter. Like, pretend there's an arrow like that, going like that, like if I was drawing it in paint. So now if count, which is equal to 0, is equal to stack size, so if 0 is equal to 4, will the 0 equal to 4? No, it's not, so it's false. So now when it's false, this brace to this brace is going to skip. Whoops. So yeah, that was our object creation. Sorry if I rushed through that. You can slow motion it. I thought we were here already. So then that's going to skip, as we said. So just skip from that brace to that brace. Now it's going to set our node, which is this node, dot set next. So our node's next reference, which is null, and top, right now it's null as well, because top was set equal to null in our constructor. So node, which is our node that we created, dot set its next reference to point to top, which is also null. So basically it's unchanged. We should see node's next reference still say null, which it is. So nodes, I'll try to do a diagram for this one as well, just to show you. So then we're gonna, so node dot set next to top, we just did that. So as you can see here, next is still null, so node that we're creating right now, it's referencing this node because it's the only node in the scope. So node at 956, so only one here, I think. Yeah, it is the only one here. So top, we're going to set now top, which is still pointing to null, our top node. We're going to point it to the node that we just created at 956, and we'll see that part. Instead of top equals to null, it should say top points to node at 956. There you go. Top now points to linear node at 956 at memory location 956. Then count plus plus. So now we have our link stack, our link dropout stack. By the way, I was going to call it link dropout stack, but the name's kind of getting long, so we just left it like that. So we have our instance data for our dropout stack. We have count equals to 1 now. We have the top pointing to at 956, which is this node that we just created. Its next reference, so node at 956, the only node on the stack. Its next reference is to null, is null of course, because there is no other node on the stack, and it's holding 5, the string 5, and that's it. So I guess we'll do this one as well. So dropout stack.push, the string 6, we'll step into it. Then here I guess we'll step into this as well. So we'll create a linear node of generic type T. Node points to a new linear node of generic type T. We'll pass in 6 this time. The string 6, we'll step into it. So every linear node again has a next has a next reference and an element reference or a field. So every linear node has instance data, a next, and an element instance data. So a next element, next field, and an element field. I'm just going to call it fields from now on. So the constructor is going to take the one with the parameter because we passed in a parameter here. So it's an overloaded constructor. So it only has two choices. The one with the parameter, there's only two, one without a parameter and one with a parameter, so it's gonna, the compiler is gonna go with this one. It's gonna set this dot element equal to element, so 6 is set for element, and next points to null. That's done. So our node's created here. Now it's at 990, not at 956. It's holding 6, and its next reference is null, and you can see here top is points to the node with which is holding 5. So if count, which is 1, is equal to stack size, which is 4, so that's false. Again, it's going to skip from this brace all the way down to here. Node.set next to top. Whoops, after we click it. So yeah, so step into that. Then node.set next to top, so node set its, so at the node at 990, set its next reference to what top is, and top's the node at 956, which is the only node on the stack right now. So it's saying take your next reference, which is technically a previous reference as we said, and point it to the node at 956. So it's basically taking one node and stacking it onto the other, like pretend they're cubes. It's taking one cube at 956, which we already have, and it's going to take the one we just created at 990, put that cube on top of that one, and take the next reference and point it to the cube below it. So that's what's going to happen. So node.set next to the top node, and right now top node's at 956. So now this reference should point to this line. Instead of saying next points to null, it'll say 956. There you go, next points to 956. Then we'll say now change the top reference to point to the actual top node, which is the one we just put on the stack. So it's going to say top points to node at 990 because it's referencing this node in the scope that we just created. So now hopefully you understand. Now the top node is now node at 990, so it's changed from at 956, it's now at 990. Then we're going to increment count by 1, so now count is going to be 2. And that's done. We're going to skip these two because we get the idea. It's going to do the exact same thing we just did now. For push 6, so we'll step over, we'll push 11, we'll push 13. So here we'll see, we'll also step over that. So here we can see our top. We have new numbers, new memory locations. Okay, so we have the node on the bottom, which is 5, of course, at 956. And then we have node, the one we just did, at 990, which is 6. Sorry, this one's 5. This one's 6, I believe. Yeah, so at 956 is 5. At 990 is 6. Then we have at 999, that's 11. And then we have one more. Which is our top, and that's 13. That's node 1001, so 1001. So now we're going to push 10 million on the string 10 million onto the stack. So here we're going to create a linear node of generic type T node. We're going to do that again. We've already done it, so we'll just run through it. So then we'll say, okay, we're at this condition now. If count, which is 4, is equal to stack size, which is also 4, that's true. Then instead of skipping it like the last times, this is the first time in this stack that it's going to be true, because the size now equals to the count. We'll step into it, skip this I guess because it's equal to null, but we have now a temp node which you can't see. This one we can delete the comments here. So then we'll say so we have this temp node object reference variable is pointing to null, but then now we'll say, okay, temp node point to top, which is the last element that we pushed on, which was 13. So if we see here top, click on it, it's holding a 13 string. So temp node now points to top. So temp node is now pointing to that 13. Because top's really pointing to a node, which is at 1001. It's pointing to a linear node. So top is pointing to the linear node at memory location 1001. So while temp node, right, which is pointing to the top node, dot get next. So I think I'll just do that down here. So or actually I'll try to do it in here. So while temp node dot get next, which is at 990, does not equal to null. So its element is 11, it's not equal to null. So while temp node dot get next does not equal to null, so it's pointing to a memory location here we can see. So it's not null, that's true. So and temp node dot get next, so temp node dot get next, which is at memory location 999, which is holding the element 11, dot its get next, so click here, next. Now we're at memory location at 990, which is 6, does not equal to null. Then temp node points to temp node dot get next, so temp node points to, sorry, what's temp node is 13. So we'll say 13. We'll say that's temp node. Then we'll say, so while temp node, so that's all we got that, that's all fine. So then temp node points to temp node dot get next, so temp node points to temp node dot get next. So temp node points to 11. Whoops. Temp node. Then we'll delete this one. So we just did that. Actually, we technically didn't. Where are we? So we're at this line. We'll jump into it. So temp node points to temp node.getNext. So now it's going to become 11. So we'll step into that. There we go. Sometimes you have to click it twice because it's going through, I think it's glitching because it actually goes get next and then there's like 2 but it only hits 1. That's okay. IntelliJ has a few glitches here and there. So then now we're at the condition and we can see temp node changed. So temp node should be 11. Yeah, so it is 11. So we'll close all these. So temp node is now 11. Right here we can see before it was 13. Okay, so while temp node, which is 11 dot get next, does not equal to null. Well, it's not null because it says, hey, linear node is pointing to memory location at 990. So it's not saying linear next equals to null, it's saying it points to at 990. And temp node dot get next does not equal to null, so it's saying, hey, this is also not null because it's pointing to memory location linear node at 956. Then temp node, well, I should actually step in. Temp node points to temp node.getNext. So again, temp node's at 11. Temp node points to temp node.getNext. Temp node points to temp node.getNext. Right there. Temp node points to temp node.getNext. Right there. And that is 6. So we'll say that's temp node now. And it's not 11 anymore. Then we'll step into that, so we'll see it change here. So now we should see temp node change to 6. There we go, temp node change, so that's closed. Then we'll open it, we'll collapse it or whatever. Then temp node now points to right here, temp node. The element for temp node is 6. So there we go. So now it's a while loop again, so we're at the condition still. We're almost done here. Should be almost done, so then we're at the condition again. So while temp node, sorry, just gonna take a little sip of water again. Excuse me. Okay, so while temp node dot get next, so we're at here, temp node points to 6. So while temp node dot get next is not equal to null, so next we're gonna click on it. Actually, we don't need to actually collapse it, so While temp node.getNext does not equal to null, so it's not null because it's saying, hey look, linear node points to memory location at 956. So that's true. And. Now we're going to check the second part. And temp node, which is this, .getNext, temp node, .getNext, does not equal to null, so that's false. So that's false. That should be false. We set our stack size is 4. So if we're adding, so yeah, so we're on the third element, so we're gonna drop the fourth one. That should be fine. Yep, so we're right. So temp node, which points to 6, set its next, which is pointing to 5, to null. So it's going to set it to null because it's going to delete it. So it deletes by setting stuff to null to take its object and just basically just set it to null, take the object away. So temp node, which is pointing to 6, take its next and set it to null. So its next is 5. So that 5 is going to be gone. So here we go. We're going to step in. Next points to node, so that's all fine. Node is null. So there we go. Temp node, which was pointing to 6, its next is now null and that 5 is gone. Decrement count. Count is 3. Node.setNext, which was our node. Okay, yeah, so I guess this was our node 10 million from before. So again, we created this node, we passed in the string 10 million into it. Then we went through this if the count is equal to stack size, if 4 equals to 4, well before, I think I said if count equals to 5, it should have been 4, but that's okay. So if 4 equals to 4, then we stepped in here, that was true, we just went through that loop. Then we're back at that node that we created, so we're saying node.setNext to top, so it's going to say what's our top node currently. Our top node currently is 13. So we have 13, 11, 6, and 5. Well, we had 5 before. 5 was dropped. So we can just keep it like that, and then so we're saying then we have 10 million here at the beginning. 100,000, 10,000, 100,000, million, 10 million. So 10 million. Take its next. Take its next. Take node that we just created and set its next reference to top. So what's top? Top is pointing to linear node at memory location 1001, which is 13. So it's saying take 10 million and take your next, which is actually a previous reference, and point it to 13. So node right here, it's take your next and point it to that one, 13. There we go. nodes next now is set to that 13. Top is still 13, so we're going to say, hey, look, now this 10 million is pointing to 13. Well, top is now not 13 because there's something on top of it, so we're going to say, take the top node reference and point it to the node that we just created right here, node at 1106, which is the element 10 million. So now we have top pointing to 10 million. We'll go over that in a sec, count plus plus. And that actually disappeared. I wanted to show you guys something, so let's just go, excuse me. Let's just go here, debug it, then we'll step in, step through, oh no, not back there. Okay, stop that. Actually, we'll just push something, just pretend. Drop stack.push. We'll just push on test. We'll debug that. Then where we went, we should go where we just left off. I just wanted to show you how the stack is looking. So here we start the stack at top, which is the numbers change now. The memory locations change every time. So we have 10 million on the top node. Whoops. Then we have, so 10 million is our top node. And we'll take the next reference to that is 13. It's the node with 13 on it. Then the next reference to that is the node with 11 on it. And the next reference to that is the one with 6 on it. So you can see 5 got dropped because it's null. So that's the difference between this one and the link stack. But that's how the linked lists work. That's how you look at them through the next reference. It's not like it's linked list and then it has all the nodes like an array. It's kind of hidden. So now we'll just do the last one. Peak, it's easy. Just returns the element, so we don't really need to go through anything. Is empty, same thing, just returns the count, size. It just returns true if count is less than or equal to 0, so obviously this is going to return false if we call it because it's not empty. Size is going to return count, so it's going to return 4. And then toString, we just did a long traversal, so we don't really need to go through it. We did a extra hard traversal, so excuse me. So let's just pop 1 or 2. So it's already been an hour and 10 minutes almost, so we'll just getting kind of tired. So dropout stack .pop, save it, put your breakpoint on it, and then debug it. Actually, we'll just stop that for a sec. Take out test, the string test. Delete that, and then we'll just go back here, debug it. So we have our dropout stack here, different memory locations. So step into pop. If is empty, so is it empty? So step in. It's going to go to is empty. So returns true if count is less than or equal to 0. So is count less than or equal to 0? Well, it's 4 So is 4 less than or equal to 0? Is 4 less than 0? No, it's not. Is 4 equal to 0? It's not, so that's false. You can step in or step over. You can, same thing there, you can step in or step over. Excuse me. So, we create an object reference variable here, temp or temp node, whatever. We're going to set it to point to top. So right now top's the memory location at 983, which is holding the string 10 million. So we're going to set temp to point to 983. So as you can see here, temp now points to 983 because we set a pointer. Then we're setting another pointer here basically, so of type T. So tval points to top.getElement. So top is 10 million, so it gets that right here. Excuse me. So val points to 10 million. So now it's saying top points to top.getNext. So top is 10 million. So top points to top.getNext. So memory location at 984. So top now points to 13. And temp points to, sorry, where's temp? So temp's pointing to 983, which is 10 million. So it's going to say, hey, take temp, which is pointing to memory location at, where are we? Temp, up here, 983. So take temp and set it to point to null. There you go, it's going to disappear. Temp is now null, so temp was actually pointing directly to memory location at 983 through top, through the previous top. So top was pointing to 983. I know it can be a little confusing at first, but just think of it like temp is controlling top. So right here, object reference temp points to top. Take the top.getElement, then top points to top.getNext, so perform a little traversal. Top points to top.getNext, which is now 13, I think. Yeah, so the top changed from 10 million to 13. Then we're going to set that pointer that we created. That was pointing to memory location at 983, which was 10 million. Take that memory location and point it to null. So basically that means just delete the object from memory. And then take count minus minus. So decrement count by 1. So it was deleted from memory, and we're going to remember to change count so that everything stays in sync. And then we're going to return val. So that's it. We changed top to point to our new memory location before we did we do it before? Yeah, before we set temp to point to null. So it changed. We reset our top, so that way we still have our linked list intact, I believe. So we'll just double check. 13. Its next points to 11. Its next points to 6. And that's it. So what we did is we popped 10 million, and then now we only have 3 elements on the stack. So I hope that helps, and I'll see you guys next time. Take care.